Hello everyone, I'm Salman Ibn Yunus. I would like to welcome you all in my in this thesis defense presentation. I'm Salman Ibn Yunus, an MSc student in the Department of Computer Science and Engineering, Brack University. I would like to thank all of you for attending this defense presentation. To all the examiners, good afternoon. Assalamu alaikum. So the title of my thesis is ECARRNet, a deep learning model for railway fault detection. Let us first take a look at the summary of contents in this presentation. So first of all, we have introduction, motivation, dataset overview and pre-processing, model architecture, explanation, model training and evaluation, explainability and visualization, results and comparison, then a bit idea about real world application, and then we conclude this presentation. I would like to start this presentation with a real world event that happened last year on 3rd May of 2024 at Jaidapur, Ghazipur. There was a collision of a train with an oil train with another oil train, and lots of people died. As you can see from the image, the devastated state of the train. So lots of people died and uh, led to a loss of financial loss as well. So from the news sources, we can see that we can know that the primary cause for such events are because of the deteriorating railway lines. So why I have decided or chosen to work with railway fault detection? So there are some statistics, recent statistics, that from the same news that I was showing the picture in the last slide. So it shows that 63% of train accidents in Bangladesh stems from track defects, as reported recently by Dhaka Tribune. And also, according to unofficial sources, there are more than 3,400 kilometers of railway lines across the country, across Bangladesh, of which only 1,000 kilometers are in good condition. Also, a comparative analysis of accidents was performed in Bangladesh in 2008 to 2014, where among 18,771 accidents have been recorded, and of which 12% took place on railways. So, we need to do something so that accidents can be reduced. We just cannot sit idle as a human. We need to do something and take some initiatives. So the first initiatives which people take are manual inspection. So as we know, people will go through, will walk or take a like transport or anything, and then we'll check manually. But this is very slow and labor intensive and often cause error because people will not. It will is very difficult to concentrate and run over such a huge track of railway in Bangladesh. So what we can do? So here AI brings a big promise because it is scalable, consistent, and will allow real-time monitoring. So the objective of this research is to develop a robust, high-performing algorithm which is tailored to railway fault detection. The target faults are rails, that is the cracks in the cracks and fastener anomalies like missing clips which hold the railway lines. So we have tried to leverage a ensemble or a hybrid model of using convolutional autoencoder, SNet, and LSTM. So as you can, this is the data set. So the second one is the called the rails, and also you can see some of the fasteners. So this is the two type of faults that will be working, that we have worked in this research. So some of the difficulties that we faced are there were lack of adequate data set on the internet and other on the online repositories and other places. So we have to collect physically by visiting multiple railway tracks in Bangladesh such as Satkira and Feni. So we collected data from old, new and abandoned railway tracks. So we have collected total images of 428 where defective are 156 and non-defective are 272. As you can see, we have usually the defective lines are fixed, so we couldn't find enough defective image. Also, it was very difficult task to collect more images manually. Even even to collect images was difficult, so we couldn't collect enough image. A small team, so that was, so we had to do some data pre-processing and augmentation to handle this problem of less images. So we have used offline augmentation, like before training. This is before training. We use vertical free rotation, brightness range, resize, and these kinds of things, and then we save those data sets. So since we have used four types of augmentation, so the data set size increased four times, and we saved 712 images. But still, the data set is not enough. So we took the help of online or in-code augmentation using Kera's image data generator. So in this case, the augmentation is performed on the fly during training, so no extra memory or physical location is occupied. So here there are five transformations have been performed. Similarly, horizontal flip, brightness range, zoom range, shear range, and resize. So after this, we it got around 8,500 images, and then we created different dataset versions. Like defect, we with rails we create one image with defective and non-defective image. We create one dataset, then we create dataset with fasteners. So there's only fasteners with defective and non-defective image, and then we combined rails and fasteners to create another dataset. So we also did region of interest cropping, so that we have don't have background things in our image, like which are irrelevant. So we extracted regions of interest from raw images, then we splitted the rest into training, validation, and test sets. Also, then we faced another problem, that is class imbalance problem, which we had to handle. So we used synthetic minority oversampling technique to increase the size of the minority class, which is usually the defective class, as we have seen initially. So we also took some other techniques used, like stratified careful shuffling to maintain equal class proportions after training. I mean, during the split, so that equal class proportions are maintained, and which reduces sampling bias and enhances experimental validity. So stratified shuffle speed actually maintains the proportion of classes that exist in the overall dataset, ensures that both training and testing subsets are representative of the entire dataset's class distribution. So the first part, important part of the ECARRNet model, which is in ensembled convolutional autoencoder ResNet based recurrent neural network, is convolutional autoencoder. So what does convolutional autoencoder do? It learns to recreate input images through a low dimensional code. It denoises and compresses data without supervision. It's an unsupervised learning technique. It replaces fully connected encoder or decoder with convolutional layers, max pooling in encoder and upsampling in decoder for special feature learning. So in encoder we have used three convolutional layers. One has 128 neurons and 6 by 6 filters, another has 64 neurons and 4 by 4 filters were used, and another has 64 neurons and 4 by 4 filters were used. And also three max pool here with 2 by 2 3 max pool layers have been used. This is basically the encoder structure, and this also contains batch normalization dropout after each layer to speed training and to regularize to reduce overfitting. So decoder also mirrors the encoder, so it has two D upsampling layers. So it has convolutional layers containing 64 neurons, three convolutional layers basically, 64 neurons, 128 neurons, and the final is one neuron and a sigmoid activation function. So it also has 6 by 6 filters, three 6 by 6 filters to recover original dimensions. So it uses normal kernel he normal kernel initializer to mitigate vanishing gradient and enable higher learning rates. Batch normalization cuts training step by step by approximately 14 times. Batch normalization cut training stays by approximately 14 times and reduces internal covariate shift for faster convergence. So then we have a ResNet backbone, which is basically utilizes Inception ResNet V2, which have been pre-trained on ImageNet to leverage rich transferable feature representation. So basically here we're using transfer learning because as you have seen that the dataset size is also small, so we need to use the trained weights from models which were trained on ImageNet so that we can utilize those weights to get a good accuracy. So it combines inception modules with ResNet style residual connection for efficient gradient flow and accelerated convergence. Residual links are built from convolutional plus tree layers to speed up training of deep inception networks. Also, it applies batch normalization to traditional convolutional layers to speed up training, as we have discussed earlier. So next we have LSTM. So basically, this all forms a hybrid architecture. Initially we have seen front end in the front Inception ResNet V2, where CNN extracts special features, and also backend we will use, and then we will use RNN, which processes CNN output as a sequence. So why RNN? So this is really unconventional to use RNN or LSTM for images. So basically what it does, it treats CNN features as a 2D time series or like a wave. So that creates a time dependency or temporal dependency, and to try to treat image as a sequencer. This way captures continuity and dependencies across spatial bands. So why LSTM and not vanilla RNN? So vanilla RNNs we know that it suffers vanishing or exploding gradients over long sequences, but LSTM is better. So it has input, forget, and output gate to manage a cell state to preserve relevant information. So we are using a bidirectional LSTM containing 2900 neurons, which in forward and backward passes. So these have been decided through a lot of experimentation and iterations. So it learns context from both past and future feature steps. So LSTM gating actually combats gradient issues and models long-term future dynamics. It outperformed also we experimented with GRU, gated recurrent units, and it outperformed in our and LSTM outperformed GRU in our railway defect dataset, boosting classification accuracy. So this is basically the model architecture. The first stage includes the encoder, then the bottleneck and the decoder, and then inception ResNet v2, then flattened layers and Gaussian noise layers. Then we have bidirectional LSTM and then some dense layers and ReLU layers. So this is basically the whole structure of our model. So as you can see, initially convolutional max pull it down to 128 into 128 feature maps. There are bottlenecks which compresses features into a 512 dimensional embedding. Also decoder head convolution ReLU upsampling as we described earlier, convolutional plus sigmoid for reconstruction plus dropout. Then we have inception ResNet v2 block 1 by 32 scale for deep multi-scale feature encoding. Then Glover average pooling has been used, flatten, layer, reshaping into a sequence for RNN input. So this is all for so that we can feed our data for RNN or bidirectional LSTM. So bidirectional LSTM initially has 512 units. We drop out Gaussian noise to capture long-term spatial dependencies. Final dense layers ReLU sigmoid to produce a defect versus non-defect prediction. So let's talk a bit about training details. So for most of the dataset, we use binary cross entropy as loss function, optimizer for AdamX, optimizer as function as AdamX, and learning rate as 0.004, and batch size 32 and epoch 50. So we split the dataset for 70% for train, 15% validation, and 15% for test. So this same thing is followed in all three datasets. And for computing environment, we use framework for TensorFlow and Keras. Hardware is NVIDIA Tesla P100 GPU available on Kaggle. Training time at least 6 hours for per dataset. Let's see some performance metrics summary that I have made as a table from the this report. So as you can see that for ECARRNet, so most of them are above 90%, except a bit less for fastener defect where precision, recall, and F1 score are a bit low. So all the values are high for the combined and rail defect dataset, indicating the traverse performance on railway fall detection. So we are also showing F1 precision and recall score. So but yeah, slightly lower for the fastener dataset as I said, but still strong with comprehensive. So there is comprehensive classification report metrics indicating balanced precision and recall. So this is a comparison with the other state of the art models. So we have compared with Inception v3, Inception ResNet v2 separately and exception. So as you can see that the top we have the data for ECARRNet. So and below we have for Inception v3 ResNet. So as you can see, ECARRNet outperforms in all baseline models across all three dataset. Particularly, you will be seeing in accuracy and is competitive in precision recording of first call. So we can say that ECARRNet is the best overall performer, particularly in combined general dataset and generation rail specific defect classification. Also, exception strong among some of the baselines. In some cases, F1 score on the Fascinator dataset, if we see that exception is it slightly outperforms ECARRNet. However, ECARRNet actually does consistently does good in high accuracy across datasets, making it the most reliable model overall for real world deployment. So we have also used the explainable AI models. So as you can see that left we have used GradCam for those models and Lime for the ECARRNet model, because this is a model developed from scratch and we cannot use GradCam. In this case, there is a limitation of GradCam that we can only use for models developed from Keras and those types. So as you can see that uh, for the full the red region actually in GradCam shows that there is a that it concentrates on the fault. So as you can see on the full data set, red region is on the near the stones. For rail data set, sometimes the red region is near the fault, but on the fastener data set, sometimes for some of the models, it is near the fault. Like for exception, it is performing good for, but for other models, it's not performing that good. Like in this image, you can see the fastener is not properly identified by the model. But if you see ECARRNet, for most of the cases, it through the yellow line it identifies the fasteners, the fault, the railway track, and for most of the cases, it does pretty good in identifying the faults and defects. So here from the confusion matrix, we are doing a false positive and false negative analysis for the all the models on the comparison model. So we can see that ECARRNet has total false positive of 20 from all the data sets and false negative of 15. And as you can see in inception ResNet v2 and inception v3, they are very high in total. So for real world deployment, what we need to think. So first of all, for real world deployment, we need to increase the dataset diversity and simulate edge cases. So what can be done, like in varied weather condition, in rain, fog, and snow, the dataset should be data should be collected, and even in dark, dawn, dusk, and night. Also, multiple camera mounts can be used, like onboard, side mounted, and drones can be used for collecting more images for real world augment. And also, so model performance and robustness, we can conduct adversarial style tests, like for in introducing noise and blood to assess stability, and we can calibrate these tools to balance detection, sensitivity, and alert fatigue. Also, we need to think about real time and edge inference. On-trend deployment often lacks powerful servers. Optimizing ECARRNet for embedded hardware ensures timely alerts. So we need to prune or quantize the network to reduce latency and memory footprint. Also, benchmark inference time on target device. Example, by using NVIDIA Jetson and Intel Movidius, implement asynchronous pipelines like capture, preprocess, inference, and post-process. We can implement a pipeline so that human intervention is required less. So we have also used already we have used GradCam or Lime. And also we can introduce human in loop review for borderline case before maintenance dispatch. So we can review, human can review, and also we can, like integration and continuous monitoring and maintenance, we can create a, so we can actually keep record of all detection and operator feedback for periodic training, and we can monitor input distributions to detect domain drift and trigger data collection. We can automate schedule retraining and performance validation. So also we need to, for integration we need to provide APIs and dashboard and train personnel to maintenance for real-time maintenance and verifying output in the field. We can design dashboards and go tag defect max and severity coding. We can expose RESTful APIs or message queries for alerts to asset management platforms, train maintenance queues on, and also we can take regulatory regulation and security, perform safety analysis, enforce encryption and access control, encrypt data in transit and at rest, authenticate device and users, document validation report, and secure model version for audits. So, in future work, as we were discussing, that we need to do more for real world deployment. We need to expand our dataset to collect a larger and more diverse dataset, maybe in the daytime or the night time or the dawn and dusk times. We need to also perform multi-class classification in the model to identify more categories of track defects, and also real-time deployment to integrate the model alongside automated detection system using drones or inspection vehicles. And we can further refine ECARRNet for better generalization, faster inference on images like pruning or techniques like pruning and or quantization to reduce latency and memory footprints. So that's all from my presentation. Thank you all for your patience and understanding. If you have any questions, please go ahead. Thank you.